In cloud infrastructure, engineers constantly negotiate between two competing priorities: locking down raw data to ensure absolute security and distributing that same data widely so highly concurrent systems can access it. Running heavy cryptography directly on a storage drive forces the host CPU to process the math, creating immediate performance penalties. Conversely, forcing hundreds of scattered compute instances to access a single directory simultaneously causes traditional block storage to break down under cross-network latency. AWS solves this performance drain by pulling the cryptography off the operating system, embedding it directly into the physical hypervisor hardware using native EBS encryption. To solve concurrent access, they bypass single-zone block storage entirely, utilizing Amazon Elastic File System to handle distributed network routing. Designing high-performance environments means looking past software-level configurations. You have to understand how data moves through physical silicon chips and local subnets. Native EBS encryption is completely transparent to your EC2 instance. There are no software agents to install or manage on your operating system. Once enabled, it automatically secures your data at rest inside the volume, as well as all the data in flight moving back and forth between the compute instance and the storage array. That strict security boundary extends automatically to all snapshots captured from that volume and seamlessly protects any future volumes you restore from those backups. This zero-touch integration is made possible by a dedicated physical component, the AWS Nitro card. As data travels along the pathway, the Nitro hardware physically intercepts all I/O traffic and applies AES-256 encryption, leveraging keys securely managed by the AWS Key Management Service. These cryptographic cycles occur strictly on the Nitro silicon. They never touch the CPU cores you are renting for your primary workload. By offloading the mathematical heavy lifting to the physical network interface fabric, the system enforces strict security standards with virtually zero impact on your application's processing speed. If you have an existing unencrypted EBS volume, you cannot simply flip a switch. The operational state of a live block drive is locked. To transition data into an encrypted state safely, engineers execute a strict migration sequence. First, capture an unencrypted EBS snapshot to freeze the data. Second, perform a copy operation on that snapshot, explicitly enabling the encryption flag and assigning your KMS key. This intermediate step is the precise moment the raw data is cryptographically scrambled and secured. Third, you restore a brand new EBS volume from this locked snapshot. Because the source is locked, the resulting volume automatically inherits that encrypted state. Finally, this secured volume is attached to the EC2 instance, replacing the vulnerable drive entirely. While it requires several steps, this specific sequence guarantees a clean transition to encrypted storage without the risk of data corruption or the need for third-party backup software. As workloads grow, they often outgrow the physical limitations of single-node storage. An EBS volume is strictly bound to one physical availability zone. Large distributed applications, like massive content management systems, demand that hundreds of servers across different geographical data centers read and write to the exact same directory concurrently. Amazon Elastic File System, or EFS, solves this architectural bottleneck. It acts as a fully managed, POSIX-compliant network file system built on the NFS version 4.1 protocol. Importantly, EFS is engineered specifically for Linux operating systems. It cannot be mounted on Windows-based instances. The primary threat to any distributed file share is the severe latency and data transfer costs that occur when servers try to communicate across separated physical zones. AWS neutralizes this latency through strategic network routing. You deploy an elastic network interface, or ENI, directly inside every subnet. Instances send their NFS requests directly to this local ENI. The ENIs then pipe that aggregated traffic securely back to the central EFS pool. Because these connections happen at the network interface layer, you control access using standard VPC security groups applied directly to the ENI. By keeping the initial connection point firmly inside the local subnet, EFS transforms what would normally be a slow, highly latent remote file share into a seamless, high-performance directory. EFS requires absolutely no capacity planning. It scales automatically up to petabytes of data while simultaneously supporting thousands of concurrent clients. Tune this scale using parameters set at creation. Choose General Purpose for latency-sensitive workloads or Max I/O for parallel data processing. Then configure throughput mode. Use bursting, select provisioned for guaranteed speeds, or rely on elastic mode to automatically scale throughput based on demand. However, continuously storing massive volumes of stale, inactive data in a high-performance network file system quickly becomes prohibitively expensive. To control costs, engineers utilize automated lifecycle management policies to move aging data across EFS storage classes. Shifting rarely accessed files out of standard storage and down into the archive tier drastically reduces overhead, dropping storage costs by 75%. Effectively deploying EFS means balancing the initial network routing with aggressive automated lifecycle management to maintain an infinitely scalable structure without the infinite bill. Successful cloud architecture ultimately comes down to matching the specific mechanics of your storage medium to the precise network topology of your workload. For low-latency, dedicated single-node processing, you rely on block storage, utilizing the physical AWS Nitro fabric to enforce KMS encryption with zero performance penalties. For distributed, concurrent access, you implement EFS for your Linux environments, using local ENI mount targets to neutralize cross-zone latency and maintain high performance. Ignoring these structural boundaries guarantees failure, resulting in either impossible encryption migration attempts or catastrophic network bottlenecks. Building truly secure, highly scalable infrastructure requires looking past the basic console toggles. You must engineer your data pathways from the deep hypervisor silicon all the way up through the virtual network layer.